Good day. Today we're going to be talking about curves with parametric equations. So imagine that a particle moves along the curve C that's shown. Here's that curve C that's shown. It's impossible to describe C by an equation of the form y equals f of x because C fails the vertical line test. That is, each input x would have more than, or some of the inputs x would have more than one output y. But the x and the y coordinates of the particle are functions of time. And so we can write x equal to f of t and y equal to g of t. Such a pair of equations is often a convenient way of describing a curve and gives rise to the following definition. So just to be clear, each of these points, x, y, would be hit at one and only one time t. And you can see that again if you watch me trace out the curve. So think about this, me as tracing out the curve various times. So time equals 1, and time equals 2, time equals 3, and time equals 4, and time equals 5, and time equals 6, et cetera, et cetera. And so at each time, we're at 1 and only one point on the curve. So here's our kind of a wordy definition. Suppose that x and y are both given as functions of a third variable t. Here, that variable has a special name. It's called a parameter. And it's given by the equations x equals f of t and y equals g of t. These are called the parametric equations. Each value of t determines a point xy, which we can plot in a coordinate plane. As t varies, the point xy, which is f of t, g of t, varies and traces out that curve C, which we call the parametric curve. Here, your parametric curve is the curve shown. The parameter t does not necessarily represent time, and in fact, we could use a letter other than t for the parameter. But in many applications of parametric curves, t does denote time, and therefore we often talk or interpret an xy equal to f of t, g of t as the position of a particle at time t. Example 1, part A. Sketch the parametric curve defined by the parametric equations x equal to t squared and y equal to t plus 1. So let's start old school with a table. Now, this table is a little bit different than tables we've worked with in the past because it will include t's, x's, and y's. So we have this extra column for the parameter t. So maybe our t's are going to go -2, -1, 0, 1, and 2. Our x's will be equal to t squared. So we would have 4, 1, 0, 1, and 4. And our y's would be equal to t plus 1. We'd have -1, 0, 1, 2, 3. We could plot this just on a normal grid. And so our first point would be at 4, -1. 1, 2, 3, 4, -1. And then we're at x equals 1, y equals 0. And then we're at x equals 0, y equals x equals 0, y equals 1. Okay. Then we were at x equals, back to x equals 1, y equals 2. And then we are at x equals 4, y equals 3. And I hope, let me check one thing. X equals 1, y equals 2. Yeah. And so I hope here you can see some sort of a parabolic shape showing up. And we might ask, is this the vertex here? We might ask, is it really a parabola? Like things we don't know, but we sort of have that general shape showing up in our curve. In part B, we want to eliminate the parameter to find the Cartesian equation of the parametric equation in part A. Then we want to use words to describe the curve. And so recall that we had x equal to t squared, and we had y equal to t plus 1. And so here we could solve for our t, and we could get t equals y minus 1, which would tell us that x equals y minus 1 quantity squared. So what have we done? We have eliminated the parameter t. So there's no t's left. This won't always be possible, but sometimes it is. And then the question asks us to use our words to describe the curve. So here we should be able to see that, yes, indeed, this is a sideways parabola. Sideways parabola opening to the right. And it does indeed have a vertex at 0, 1. Where am I getting that? I'm getting the 0 from the x side, and I'm getting the 1 from the y side. In part C, we want to sketch the parametric curve defined by the parametric equations x equals t squared, y equals t plus 1. But this is when 0 is less than or equal to 2, t is less than or equal to 3. And so we could start by thinking about this like the same parabola that we had before, which when y equals 0, this would go through 1. So we have some nice curve like this. And I'm drawing it dotted for reasons that will become clear in just a moment. So we'd still need to take into account the fact that we want our t's to vary between 0 and 3. So notice that when t equals 0, so t equals 0, this would be at x equals 0, y equals 1. So that would be this point here. And when t equals 3, this would be where x equals 9 and y equals 4. So maybe some point out here, again, not to scale, here we're at here we're at 4 on the y, and 9 on the x. And the point is where t equals 3. And so if we want to start and end our curve from t equals 0 to t equals 3, just walking this part of the curve, then what we're saying is we want the parabola just in that one region. Okay. But then it's going to end. And so all the rest of the curve is going to get erased, if you will. So erase the rest of the curve, except for in the places between t equals 0 and t equals 3. So it's like a curve segment, not a line segment, but a curve segment. In general, the curve with parametric equations x equal to f of t, y equal to g of t, on a less than or equal to t less than or equal to b, has initial starting point f of a, g of a, and terminal or ending point f of b, g of b. Just to make sure it's clear. So if we're starting at a, we have initial point or starting point f of a, g of a, and we're going to b. So we end at f of b, g of b. It won't always be the case, but it's generally the case. There's an important difference between a curve, which is a set of points, and a parametric curve in which the points are traced in a particular way. So I'd like to use this next example to introduce the graphing calculator. So in example 2, I'd like to graph the parametric curve x equals 2 cosine t plus 3 and y equals 2 sine t plus 1. And this is on 0 less than or equal to t less than or equal to 2 pi. So if I want to graph this on my Texan friend, then I need to first put my graphing calculator into parametric mode. So I'm going to go to mode, and I notice that I am indeed in radian mode. That's good. But then down here, about 4 lines, I want to go over and put it in parametric mode. So now I can go to my y equals, and my x is going to be 2 cosine of t. And you'll notice because I'm in the parametric mode, suddenly the variable is a t. And I want this plus 3. And now I can go and enter my y equation, which would be 2 sine t plus 1. And I'm going to check my window. My window is the default -10 to 10, -10 to 10. I'm going to change my step size to be very small. Don't need to make, this will impact the speed at which the graph takes place. This is probably still going to be too fast for what I want. So let's graph. Oh, there it goes. So if you try the t equals 0.001, it will probably graph much more slowly than this. So you would want to have a smaller t size to see it graph. So you notice how time is passing, and as time passes, we generate the graph. At first glance, this looks sort of like a football, but let's change our window to be square. So I'm going to change this to the 5th option, z square. Give you a little bit of a sense of what's going on. So now the proportions are even. Proportions are even horizontally and vertically. So notice that what's being traced out here is a circle. If I go back to my window and I change that t step to be, say, 0.0 or just maybe 0.1, something much nicer, it'll graph the same thing, but very quickly. So again, changing the t step will change the speed and the accuracy at which something is graphed. So it looks like we have a circle, and where is that circle centered? It looks like it's centered at x equals 3, y equals 1. So let's go back and keep working on our notes. So we want to graph the parametric curve. Again, x equals 2 cosine t plus 3, y equals 2 sine t plus 1 on 0 less than or equal to t less than or equal to 2 pi. And we just learned pretty conveniently using our Texan friend that this is going to be a circle centered at 1, 2, 3 in the x and 1 in the y. So it can be centered here. And we didn't talk about it earlier, but it's going to have a radius of 2. And so it looks like our circle is going to be something along these lines. So you know it's going to be horizontal, the 2 top points, vertical, the 2 bottom points. Something like that. We saw it trace out, and we saw it trace out in a counterclockwise manner. We also saw that it started and ended kind of over here at on the right side. So it started here at, I think that would be 5, 1 at t equals 0, and it's going to end at 5, 1 at t equal to 2 pi. So we've sort of answered part B already. So in our own words, we want to describe the parametric curve, and kind of the emphasis is on parametric here. And so this is a circle centered at 1, 3 with radius 2. But then we have to talk about the parametric side of it. So that is traced out counterclockwise, CCW counterclockwise, starting and ending at 0.51. We could contrast this with just describing the curve. And so the curve itself would just be the front part of this without talking anything about the tracing and the starting and the ending. So it's just a circle with radius 2, centered at 3, or I said 1, 3 above, I meant 3, 1. So up here, this should have been x equals 3, y equals 1. My apologies. We wanted to come up with a Cartesian equation for this. We could think back to what we've done in the past. This would be x minus 3 quantity squared plus y minus 1 quantity squared equals 4. It's a circle centered at 3, 1 with a radius of 2, 2 squared being 4. So in part E, parametric equations do not uniquely represent a curve. So come up with 3 different sets of parametric equations that give you the same curve. That is a circle centered at 3, 1 with radius 2. So there's a couple ways we could approach this. So one is we could adjust the parameter. So we could have x equals 2 cosine t, y equals 2 sine t. This would be plus 3, plus 1 on 0 less than or equal to t, less than or equal to 2 pi. We could, for example, make this happen twice as fast. So if we did it 2t, 2t, and now our t's only need to go as far as pi. So that would be adjusting the parameter. We could adjust the parameter a different way. We could let x equal to 2 cosine t plus 3, y equal to 2 sine t plus 1 on 0 less than or equal to t less than or equal to 2 pi. But maybe I could shift where my t's are starting and ending. And so I could say this is like t plus 1, t plus 1. And I could shift my inequality to say where the t's live, but I could actually leave it in place if I wanted. You can test this out on your Texan friend, but if I crafted it in this manner, all we would be doing is we would be saying start at a different point and end at a different point, but it would still take 2 pi to make the full loop. Finally, we could think back to those Cartesian equations. And so if you think back to those Cartesian equations that are up above, imagine solving this up here for y. So you'd have y equals the square root of, you can have a 4 or plus or minus 4 minus x minus 3 squared plus 1. And so I could use this concept, and I could have a third definition, 3. I could let x equal t, and I could let y equal, I'm just going to use the plus version here, 4 minus t minus 3 squared plus 1. And this would be, I want to know where my x's live or my t's live. This would be on t's between 1 and 5. If you check this out on your Texan friend, you should get that the graph is just the upper half of the circle, not the full circle. You'd have to use 2 parametric equations to describe the whole circle in this manner. So there's 3 different representations for a circle, or at least part of a circle, using parametric equations. So parametric equations of the circle with center h, k, and radius r are given by x equal to h plus r cosine t, y equal to k plus sine t on 0 less than or equal to t less than or equal to 2 pi. And one thing I want to point out here is that this circle is being traversed counterclockwise, and our tracing is beginning over here on the right side. It's kind of our starting and ending point. In example 3, we want to describe the motion of a particle with position xy as t varies in the given interval. So here, x is equal to 2 sine t, and y is equal to 2 plus cosine t, and we're on 0 less than or equal to t less than or equal to 3 pi over 2. You'll notice that this looks similar to the circle formula that we were given, but notice here we have sine with x and cosine with y. So let's use our Texan friend to try to understand what's going on with this particular equation. So once again, we're going to graph using our graphing calculator. So my calculator is still in parametric mode. So I'm going to go to the y equals and enter my 2 equations. So for x, I have 2 sine t. And for y, I have 2 plus cosine t. And so we notice the 2 differences between this and the formula above. So we notice that with sines in the on the x and cosines on the y, we also notice that there's a 2 times the sine, but just a 2 plus in the cosine. Kind of the operations are different. And we want to see what happens. I'm going to again slow down my step size by changing my t-step and making it smaller. Again, just slows down the graphing process so we can see what happens. We're still with the square window. The first thing I want to point out is that the curve sketching began up here at the top point, and then it was traversed clockwise instead of counterclockwise. Let's adjust our window to account for the t's that were given. So we want our t's to go from 0 to 3 pi divided by 2. So again, we're starting at the point 0, 3, and then we're proceeding clockwise. And it looks like we're going to end over here on the far left side. The shape isn't complete, but you'll notice that the shape seems to be 4 units wide, 2 units tall. So this looks like it is an ellipse. So we want to describe the motion of the particle as t varies. So that is, we think that we have an ellipse. And our ellipse is going to be centered at x equals 0, y equals 2. And it's going to be 2 tall or 2 wide and 1 tall. 2, 2. And we want to start at the top and work our way 3/4 of the way around the ellipse. We're traveling clockwise. So if we want to describe the motion of the particle, right, the particle is going to travel, it's going to start at 0, 3, travel clockwise around the ellipse. It's going to end at, it looks like -2, 2. And the ellipse is not completed. Knowing that this is an ellipse, we can come up with Cartesian equations. That is, we can eliminate the parameter. So we remember the equation of an ellipse centered at 0, 2 would be x squared over a squared plus y minus 2 squared over b squared equals 1. And our question is just, what are the a's and the b's? And so we know that it's going to be wide. And so imagine that if we let our y equal to 2, so if we let our y equal 2, that would put us along the horizontal part of the picture. Along the major axis, and the center term would go away. So you could imagine that center term gone. Then we want to get a x squared over a squared to equal plus or minus 2. Sorry, to equal plus x squared over a squared to equal 1. And we want that to be true when x equals plus or minus 2. And so it should be clear that our a squared would have to be 2 squared or 4. Similarly, if we let x equal 0, so we were on the minor axis, then we want our y's to come out to 1 or 3, and it should be clear that the b will have to be 1 squared or just 1. So here are the Cartesian equations for this same ellipse. Notice the Cartesian equations don't tell you to skip that one little chunk of the graph. An important use of parametric curves is in computer-aided design, or CAD. A special type of parametric curve is called the Bezier curve, and they're used extensively in manufacturing, especially in the automotive industry. So these curves are also used in specifying the shapes of letters and other symbols in laser printers. Basically, computers love parametric equations. This next example, example 4, helps us to understand the importance of the t-step. And so we're going to graph on our calculator in the window -2 to 2, -2 to 2, with t going from 0 to 2 pi. And it's a little difficult to do the soft bracket, so we'll do hard bracket there. First with t-step equal to 0.1, and then with t-step equal to 0.01. And here's our kind of ugly equations. X equals sine t plus 0.5 sine 5t plus 0.25 sine 13t, and y equals cosine t plus 0.5 cosine 5t plus 0.25 cosine 13t. And we want to know what happens when the steps are smaller. So let's begin by entering our equations into our text in front. So our x is going to be equal to sine t plus 0.5 sine 5t plus 0.25 sine 13t. And I try to always remember to close my parentheses. Our y's are going to be cosine t. And then we have plus 0.5 cosine 5t. And then plus 0.25 cosine 13t. And in keeping with the directions, we'll next go to our window and we'll change our window to go from, to have our t-step go from 0 to 2 pi. But we will have our step itself go by a size of 0.1. And our x minimum is -2. X maximum is 2. We don't care about scale. Y minimum is -2. And y maximum is 2. And graph, and let's see what we get. Ooh, very fancy. Notice that the graph is not complete up here at the end. And it looks like we've got this very, very jerky, kind of like line segmenty thing happening as we travel around our curve. So that's a pretty crazy looking picture. But what I really want to emphasize is you have these line segments. There's nothing soft and curvy, even though you see the potential of some curviness here. Let's go back to our window. And as per the directions, let's change our t-step to 0.01 and graph. Oh, that curve gets a lot softer. And notice now it seems like it's complete. We might ask what's going on in these little regions here. Maybe let's just try one more graphing and see what happens. So we change our t-step to 0.001. Our graph should become even finer. It looks like there's a little loop-de-loo thing that's happening right there on the inside. Little inner loop. It's kind of a cool, pretty little shape. And one of the things that you'll note as you play around with parametric equations is that many of the pictures are quite pretty. You'll also notice that as I make my t-step smaller, it takes a lot longer for the graph to happen. So there's sort of this balancing act between precision and speed. And so you're kind of having to decide depending upon the application that you're working on. The question asks, what happens when the steps are smaller? So smaller steps sort of translate to two things. Translates to a more precise graph, so a better graph. But it also translates to more time for the graphing process. So longer calculations. As in more time. The cycloid. A definition. The curve traced out by a point P on the circumference of a circle as the circle rolls along a straight line, or any curve, your book also demonstrates it inside and outside of a circle, is called a cycloid. And there's a link here so that you could kind of play around with them yourself. Here up above is the traditional cycloid, and you'll notice that it comes all the way down to the axis and then pops back up again, and pops back up again, and pops back up again. And then below you have this curate cycloid that never makes it down to the axis. And you'll notice in the curate, the point we're looking at is on the inside of the circle. For the prolate cycloid, we very much cross the axis, and the point that we're looking at is outside of the circle. Let's look at an animation to try to understand what's going on here. So let me play it. Let me run the animation. It doesn't seem to want to let me just play it. That's a little frustrating. So if I rotate along, you'll notice that there's a point, a fixed point on the circle. So like think about a wheel, and the wheel is rotating, and we're asking what curve is traced out as that fixed point rolls along the road. Fixed point is rolling along the road. So we could ask, what does the A do in these equations? So A is going to basically adjust the size of the circle. So here we could rotate along, and now we've got a bigger circle, which is going to make a bigger kind of like bigger cycloid curve. Smaller circles, more loops. Okay. You'll notice that in the x formula that's given, there's a t variable, and that's saying that we want that t variable is what causes the wheel to move along the x-axis. So it moves this direction. That's what the t does there. The 1 in the y here is sort of telling us where is the midpoint, kind of like where's the center of the circle. And so in the x, you sort of say, we're moving along with that t, and then we have some sine cosininess that makes the circle kind of based on the circle. And in the y, you keep the y constant because you want the center of the circle to always be in the same place. And you've got some cosininess again to reference the circle. You'll notice that we're rotating our circle. Our circle is rotating clockwise. And so kind of in thinking with about what we did earlier, we remember that the sine cosine bit kind of reminds us of the clockwise rotation, whereas the cosine sine would have given us some sort of a counterclockwise rotation. There's a little bit about the picture of a cycloid. Historical note. Galileo seems to have been the first to notice the cycloid and investigate its properties. And this was in the early 1600s. He didn't actually discover any of these properties. Sorry, there's a typo there. But he gave the curve its name, and he recommended its study to his friends, including Marcin in Paris. Marcin was kind of an interesting guy in that he wrote letters to lots of other mathematicians. He was kind of like the I don't know, letter keeper. He was the Google, if you will, for mathematicians. He didn't know the answers himself, but he could always connect people to the answers. So Marcin informed Descartes and others about it. And in 1638, Descartes found a construction for the tangent of the cycloid. In 1644, Galileo's disciple Torricelli who invented the barometer, published his discovery of the area under one arch. And the length of one arch was discovered in 1658 by the great English architect Christopher Wren. Example 5. If a and b are fixed numbers, find parametric equations for the curve that consists of all possible positions of the point px in the figure. And we want to use angle theta as our parameter. So let's see if we can understand what this picture is about. So it looks like we have an inner circle with radius b, and then we have an outer circle with radius a. Okay, and then what we're interested in is something about this point P, which is sort of kind of halfway in between the red and the green circles, but it has the same, looks like it has the same y coordinate as the red point, and it has the same x coordinate as the green point. So let's see if we can figure out what the red and the green points are. So our green point would be a circle centered at the origin with radius a. We wanted to trace it out counterclockwise, so this would be a cosine theta, because that's our parameter, a sine theta. And then we have a red point, which would be at b cosine of theta and b sine of theta. And it looks like, again, we want to find the y coordinate from the red one, and we want to find the x coordinate from the green one. And so our parametric curve for this point P would be that x is equal to the green a cosine theta, and y is equal to the red b sine theta, and this would all be on 0 less than or equal to theta less than or equal to 2 pi. All right, now that we have the coordinates or a vector expression for the point where our P takes its x coordinate from the green curve, and also the point where the P takes its y coordinate from the red curve, we can put these together to find a parametric equation for point P. So point P has x coordinate, so it has x coordinate equal to the green x value, which would be a cosine theta, and it has y coordinate equal to the red y value, which would be b sine theta. So again, here's our color scheme. And we know this would be true when 0 is less than or equal to theta is less than or equal to 2 pi. Okay, so we have an expression for x and for y, and now we need to put these things together. Actually, let's graph this thing to see what it looks like. So for the sake of, I don't know, something to talk about, suppose that we graph this with our A value equal to 5, that's the outside radius, and our B value equal to 2. There's our inside radius. That should give us something interesting to help us get a feel for what this shape looks like. First thing I'm going to do is I'm going to graph the inside and the outside circle. So my outside circle is going to be at 5 cosine t and 5 sine t, since we picked the radius to be 5. And my inside circle is going to be at 2 cosine t and 2 sine t. And so let's just see what that looks like to start with. So if I do a standard window, and then we make it square so that the proportions stay nice, we have kind of an outside blue circle, an inside red circle. Ooh, just like we were hoping. So now we got to graph that point P in the middle. So to graph the point P, we go back out and we let our x coordinate come from the big circle. So it's going to be 5 cosine t, and our y coordinate come from the smaller red circle. We'll have 2 sine t. When we graph, we should get some sort of an ellipse. It's kind of a cool, almost like an eye-shaped total picture. And this gives us a sense of what we should look for in eliminating the parameter. Namely, we think that our answer is going to be some sort of an ellipse with a minor axis of 2 and a major axis of 5. So we have the graph in mind, which should help us to eliminate the parameter. But when we see that A cosine and that B sine, this should make us think, hey, maybe this is going to be an ellipse. So we're thinking this is an ellipse. So if that's the case, let's just try and see whether our standard ellipse equation would work. So let's try x squared over a squared plus y squared over b squared equals 1. So does this work? So to figure out if it's going to work, I'm going to take that teal x expression and put it in for x, and I'm going to take that yellow y expression and put it in for my y and see what happens. So if we substitute in, we will get the a cosine theta quantity squared over a squared plus b sine squared or sine theta quantity squared over b squared equals question mark 1. And the a's and the b's are going to cancel, and we get cosine squared theta plus sine squared theta equals 1, which is always true. So at the end of the day, we've eliminated our parameter. Our parameter is eliminated here with this function. And then we're also asked to identify the curve. So if we want to identify the curve, it's an ellipse. Pardon me. It's an ellipse centered at the origin. With axes of length 2a and 2b of this is what the curve is that we found. Example 6. If a circle has a radius r and rolls along the x-axis, if one position of P is the origin, find the parametric equations for the cycloid created by P, x, y. This is an interesting question that requires us to do a little bit of thinking. So one piece of thinking we have to deal with is around the circumference of a circle. So I want to start with an observation. So observe that if a circle of radius r rotates theta radians, then the total amount of arc length swept out would be r theta. So a circle that rotates theta radians and has radius r, sweeps out a total arc length total arc of length r times theta. Let me make sure you're understanding what's going on here. So I'm saying that if we, for example, started with some point here and we traveled a total of maybe, here's pi, 2 pi, 3 pi, maybe I do 3 pi and a quarter. So I've got, in this example, I went more than once around, 3 pi plus a quarter pi. Plus a quarter pi, then this is the amount of theta-ness. Then the length of that arc would be 3 pi plus pi over 4 times whatever that arc for r is. Okay, so this ends up being pretty handy for us as we try to figure out how far we've moved along the curve. Okay. Second thing we need to observe. We need to observe that if our circle is moving this direction, then that means our circle is also must be rotating clockwise. Observe circle is rotating clockwise. Cool. The third thing we want to observe has to do with the starting point. So notice that in the equation it says if one position of P is at the origin, that means at some point our circle went through the origin. Okay, and so P, we want at time equals 0, we want to be at the origin, and then we want to travel counterclockwise, or clockwise, I should say. So observe at theta equals 0, or time equals 0 if you want, the point P is at the origin. So let's play around a little bit with our Texan friend before we keep going on with our derivation. So what we would like to find here is we would like to find a way of representing a circle that where we're representing our circle parametrically in such a way that it begins, it rotates clockwise, not counterclockwise, rotates clockwise, and we would also like it to begin at the bottom point, the lowest point. And so let's just play around with a nice friendly circle. So if I take cosine of t, and I have sine of t, sine of t, then our graph, it's a little fast. We need to slow down that t step. I'll change, I want to see what's going on, so I'll change my t step to 0.001, slow it down. And we notice everything is really small. We could zoom in, but maybe rather than zooming in, perhaps we could simply expand out our circle. Or zoom in, I guess. Zoom in. Nice. So there's our circle. We notice that this is rotating counterclockwise, and it's starting on the right side. We want to be clockwise and starting at the bottom. So we figured this out somewhat earlier, when we realized if we swapped our sine and our cosine, things get a little bit better. If I swap my sine and my cosine, the graph, now we're running clockwise, so our direction is good, but we're starting at the top when we want to start at the bottom. So we want to start at the bottom. Well, let's go back up. We could do a couple of different things, but one is we could ask, what happens if we just reversed the signs? Because really we know at our first point, x is 0, and we want our y to be negative. So if I tried inserting a negative on the y, see what happens. So now I'm starting in the right place, but again, I'm going counterclockwise. We want to be going clockwise. What I like about this example is you kind of get the sense of the back and forth of knowing roughly what you want, but not having an exact idea of where you're going. So let's try inserting another negative and graphing. Oh, here we are. We're starting at the bottom, and we're running clockwise, which I think for you would be this way. Pretty cool stuff. All right, so what I want to observe next is, so far, let's see, what we just came up with is that if we want to go clockwise and start at the bottom, then we want something like x equals minus sine theta and y equals minus cosine theta. Okay, so that's what we got out of our Texan friend interlude. So now let's observe that the center of the circle, will have a y value at y equal to r. We'll let us shift the circle up a little bit. So that's pretty nice. And so we've got some circle that is centered at y equals r, but then we want to be able to always, from that center point, we're going to then adjust based on where on the unit circle where our point P is. So at this point, I want to separate out the x's and the y's and kind of think about them individually in this picture. And I also need to make a correction. Notice when I talked about my x and my y coordinates over here, these would be both times r, because we need to account for the radius. So next up, we're going to focus on the x. We want to focus on the x. Our x coordinate is going to, roughly speaking, be on the basis of how far the wheel has rolled. So like it's going to be moving along the x-axis. And we know that the distance it's traveled along the x-axis is r theta from our earlier observation. But it's not exactly at r theta. We also have to account for where the point P is. Like the r theta will be telling me where the will be giving me the x coordinate of the center. Here's my r theta, and then I need to adjust for the x coordinate of the point within it, and that's given by the minus r sine theta. So I have minus r sine theta, or in other words, r times theta minus sine theta. My y's are coming from the center of the circle. The center of the circle is here at y equals r. So we know we're going to have an r. And then that only gets us to the center here. But we want to be able to go up or down based on the y value that we found earlier, which would be minus r cosine theta. So then we would subtract out r cosine theta, or we could factor it out and we would have r times 1 minus cosine theta. And both of these equations would be true for all thetas, but we would have one full cycle of the cycloid, full cycloid cycle on 0 to 2 pi. So here at the bottom, we have those equations of the cycloid. We get, again, the x equals r times theta minus sine theta, y equals r times 1 minus cosine theta. And notice here below, we have theta on the real numbers, and that's because that wheel can keep spinning over and over and over and over again. Each arc of the cycloid corresponds to one rotation of the circle. We could also write the equation of the cycloid in terms of x and y, but it's kind of awkward. The Cartesian representation, and I give you that Cartesian representation here, it works, but it's a lot less elegant than the cycloid equations that we just mastered above. So there you have it, everything that you need to know about parametric equations.